Good morning. Here's today's starter. So it's a starter on Pulleys Year 12 question. So have a look at this and make sure that you can do it. So have a quick look. Obviously, we're not teaching pulleys today. So here's your question. And again, it will be on your PDF. So there's your diagram and your questions. 5-mark exam question. And here's your mark scheme. So if there's anything you're unsure of about pulleys, please ask. So now's the time to get help. It's going to be on your Year 12 assessment. So what we're looking at today, infinite geometric series. As you can see here, infinite sequence continues forever. Adding up the terms in a sequence forms a series. The sum of an infinite arithmetic sequence, so an arithmetic sequence is where you're adding on or taking off the same term each time. The sum will be infinite, either positive infinity or negative infinity. Same with a geometric sequence. Sometimes, if you take an infinite geometric sequence and add up the terms, the sum again will be positive infinity or negative infinity. But what's different about geometric sequences to arithmetic sequence is sometimes when you have an infinite geometric sequence, you can actually find the sum to an infinite number of terms. And this will be when you have a sequence that converges to a limit. That's what we're going to look at today. Let's consider some geometric sequences. Here's a really nice one. First term 1, common ratio 2. You can see that this sequence is diverging. It's just going to get bigger and bigger and bigger. So the sum of its terms would be positive infinity. You can't find it, it's no good. Let's look at this next one. So first term 10, common ratio -2. And you can see, although it's sort of alternating signs, it again is diverging. You can't find the sum of this to an infinite number of terms. However, this sequence here, its first term is 12 and your common ratio is 0.5. You can see that these terms are heading towards a limit. That limit is 0. And because this sequence is converging, you are going to be able to find the sum to an infinite number of terms. This question here, first term 40, common ratio -1/4. So they're oscillating in signs, you're going positive, negative because of your negative common ratio. But again, they are heading to a limit. And again, they're heading to this limit of 0 here. So this is a convergent sequence. You would be able to find the sum to an infinite number of terms. So what we notice, and we can go into a bit more detail with this, in fact, if you think about the binomial theorem that we've done in year 13, the binomial theorem and infinite geometric sequences are really strongly linked. And just as you have a condition for your binomial expansion to be valid, here you have a condition on your common ratio so that a geometric sequence will converge. Your common ratio has to lie between 1 and -1. It can't equal 1, because if it equaled 1, your terms would just stay the same. But your common ratio, if your common ratio on your geometric series lies between 1 and -1, sometimes we write it using a modulus sign, then your sequence will converge. Whoa, didn't mean to do that. So, okay. Proof. Now again, you don't need to prove this formula. You're going to be told it in the exam. You don't need to prove it, but it's quite interesting for a lot of you, especially those of you, it's just generally interesting, especially if you're thinking you might want to do maths at university or go into that kind of world, engineering. It's really nice to see where these results come from rather than me just tell you. Obviously, if you don't want to know, just let me just tell you, okay? And you can sort of ignore this little bit of a proof here. You know that if n lies between, if a number lies between 1 and -1, like 0.5 or 0.6 or -0.3, if you raise that number to a huge power, so 0.5 to the power 12, it gets really, really tiny. It gets very, very close to 0. So the result that we're going to use today comes from the one that we've already met yesterday. So here's our sum to n terms of a geometric sequence. If you know that r lies between 1 and -1, which it has to be able to have a convergent sequence for you to be able to find the sum of it, and you raise that to an enormous power, which infinity is, you're finding the sum to an infinite number of terms. If you take a value here, and raise it to an enormous power, it will tend to 0. It will become so tiny that it is of no consequence at all. So if you replace your r to the n with a 0 in your formula, you're just going to get a times 1 on the top. So here we have our new formula today. To find the sum of a geometric sequence that converges, we have our first term a divided by 1 minus r, and again this is only if r lies between 1 and -1. This again will be given to you on your exam formula sheet, so you don't have to learn it. Obviously you need to know it, and you need to know when to use it. Right, example 1, and this is the little clip from your exam formula sheet that there will be. So for the geometric sequence or geometric series, they've called it a series because they're adding the terms together. You've got 16, your first term's 16, your second term's -4, your third term's 1. Find the sum of the first 4 terms. Right, I think this is quite an interesting question, because would it be quicker literally to just go 16, take away 4, add 1, take away a quarter? So you could do that because you can literally see your first 4 terms. Obviously, I'm gonna use the formula because we're still learning that, I suppose. But you don't have to use the formula for this first one. So a is 16 and r is -1/4, which I've written as a decimal because I'm doing this on my computer and it's easier to write. But then if you pop them in your formula, so the sum to 4 terms is 51/4, which is going to be just under 13, isn't it? 12.75. Again, you could have just physically added those up. And now I'm going to find the sum to infinity, so I get my new formula. And I know that's okay. Whoa, you can see what I've done there, can't you? I've moved my little thing out that I doctored. That's better. So substituting in our values into our new formula, the sum to an infinite number of terms is 64/5. Now that's pretty interesting, isn't it? Because the sum to 4 terms is 12.75, and the sum for an infinite number of terms forever and ever is only 12.8. And the reason there's not much difference between the two is because after the 4th term, they become tiny. Your terms are so tiny, so that hasn't made much difference. Right, so if you'd like to pause the video, and what you're going to do is you're going to find the sum of the geometric series to infinity if you can. So first of all, decide what the common ratio is. If it lies between 1 and -1, find the sum to infinite number of terms. If it doesn't, you've got a divergent sequence. So have a quick go at those. And here are your answers. Okay, example 2. We're going to find the sum to infinity of a geometric series. The sum to infinity of a geometric series is 5, and its second term is minus 6 over 5. Find the common ratio. So it's not asking for the first term, which of course you would then be able to find. So it's going to be an algebra-based question. You know the sum to infinity formula, so that's fine. Substitute that in 5 in there, and you know the nth term of a geometric sequence. You've learnt it. So the second term will be a times r to the 1. So a times r is minus 6 over 5. And now, basically, it's your personal preference about how you would solve this. You might want to make a the subject here and rearrange. I've chosen to divide both sides by r. I haven't really, I've copied this out of the textbook, so I've gone with their method. So we make, whatever you do, you make a the subject. I've then substituted this, or they've substituted this into here. And then they've rearranged and they formed a quadratic in R. Whatever happens here, you're going to get a quadratic in R, whichever method you use. So there's your quadratic. Again, if it doesn't say show detailed reasoning, pop that in your calculator and you can see that there you have your two values of R. Now, there's no reason, there's no, in normal geometric series, there's not really any restriction on R. However, in a convergent geometric series, there is. You know that the sum to infinity can be found of this geometric series. So that means R must lie between 1 and negative 1. So this is not a valid R. So since that exists, so we know that your common ratio must be minus a fifth. It's a good question. Right, and then obviously what's going to happen is you've got these formulae, you're just now going to sort of make them more challenging. So the geometric series, so the term 2 minus x plus 2 minus x all squared converges. So this tells us an enormous amount already. We know the first term is 2 minus x. We know the common ratio is 2 minus x. And we know that common ratio must lie between 1 and negative 1. So to find the possible values of x. So get your common ratio, 2 minus x. That lies between 1 and negative 1. And now you've got a two-sided linear equality to solve. Really a bit of a nasty GCSE question. So what I'm going to do, it's up to you how you solve this, but I'm going to take 2 off both sides, and I know to make that minus x, positive x, I'm going to multiply or divide all through by negative 1, which means I invert my inequalities. So just be careful there. So x is actually less than 3 and greater than 1. That's because I've multiplied all through by negative 1. Right, here are some questions to do. So if you pause the video, and then a little bit of a horrid question there, where you're going to probably have to use some sort of log idea. So there are your questions. Here are your answers, and I'll see you tomorrow.